Swayam Prabha. Digital India. Educated India.
So now we'll talk about pump probe. Let's go back to pump probe because we have some unfinished business, but also we want to figure out some, we need to kind of come up with a motivation to do 2D spectroscopy. So let's start with pump probe. So let's take a scenario now. So I'm going to put out a particular scenario. We have so far worked only with 2-level systems. Let's say we'll work with a 2-level system, but with vibrations. Which I annote with 2 sort of parameters. So 0 ground state and 0 vibrational state, 0 electronic ground state and first vibrational state. This is the first electronic excited state, 0th vibrational state. And this is, let's say, first electronic state and first vibrational state. Of course, there will be other vibrational states, but let's just consider this simple scenario. Okay, so I could write, for example, for pump probe, we have already seen double-sided Feynman diagrams, which will talk about population, right? We all know this. For example, I can write a scenario where I go from 0, 0, 0, 0, then I come with my fields, then I go to, let's say, 1, 0, 1, 0. Then I could have a de-excitation. Then I'll have 1, 0 and 0, 0, which will emit. So what is the associated feature in pump probe with this Feynman diagram? We spoke about at least 2, 3 features, right? What are the 3 features in pump probe signal? Ground state bleach and photoinduced absorption. There is also stimulated emission. What would this be? What would this be? You can be loud. This will be a ground state bleach. You're generating a population and measuring the coherence from that state, right? So you're measuring that. You're measuring the ground to the excited state coherence going through a population dump. So this will be a ground state bleach. And ground state bleach, dynamics of that, of course, will, because your pump probe delay is between these 2 interactions, right? That's your pump probe delay. And that will depend only on the population. Right? This is a population. Where is the population? My population is sitting here. That's my population, right? So that will simply be an exponential decay dependent on the lifetime of the population in the excited state. Agreed? So what you would expect to see in my pump probe signal, which is some delta I, delta T over T or delta R over R, whatever you might say, in time, you will see a decay. And that is related to the population lifetime, nothing to do with coherence. Remember, it's generally not possible to access coherence using pump probe. I'm not saying impossible, typically it is not possible. I'm going to draw one more Feynman diagram, and you should be able to predict how this Feynman diagram or the response of this Feynman diagram will look like. I'll start again from 0, 0, and that corresponds to, and then let's say I'm going to split out the first two interactions for the sake of convenience. So I have my first interaction. Let's say I go to 1, 0. My second interaction, but it's still within the same pulse. So my first interaction is not, in the ladder diagram, it goes from 0, 0 to 1, 0. So 0, 0 to 1, 0. That's your first one. My second interaction, which also happens while the first interaction is happening, is from 0, 0 to, so let's put it here. Let's say I have it going to 1, 1, 1, 0. So second one is going here. So the two field interaction, what did it generate? Did it generate a population? What did it generate then? You agree with me, it generated a coherence. What kind of coherence? Vibrational coherence. It's between the 0th vibrational state in the excited state and the first vibrational state in my electronic excited state. I see, make a coherence between them. Okay? And how will this coherence evolve? It's a coherence. Coherence will oscillate and damp, of course. And it will oscillate at what frequency? Energy difference between the two states. And the energy difference between the two states will be the energy of the vibration. So when I measure this response, what do I get? I will get some oscillation, which will of course damp on top of the population. Population is also there. But also get this, of course, to complete the Feynman diagram. I should also write this. Okay. So you can generate coherence response in pump probe signal, but this is coming from vibrational coherence. And you can measure phonon energies, vibrational energies. This is similar to doing a resonant Raman experiment. It's a Raman scattering process, but done in time domain. Right? Now this particular diagram, I'm seeing vibrational coherence in the electronic excited state, right? I'm seeing the vibrational coherence in the electronic excited state. But is that the only contribution to pump probe? No, because I could have, or I will have, another Feynman diagram which will generate vibrational coherence only in the ground state. Can you come up with that? I'm giving you already information that I will have a Feynman excitation pathway, a Liouville pathway, which will generate vibrational coherence in the ground state, not in the excited state, which means a coherence of the form 0, 0, 0, 1. What would that Feynman diagram look like? Remember, in pump probe, you can have contributions from R1, R2, R3, R4 correlation functions. All of them contribute. So you can use all of them. Any of them, sorry, not all of them. So I start from 0, 0, 0, 0. Let's say this time I go from the get side. Create 1, 0, and 0, 0. If I come from this side, I'll start going to excited state. I don't want to go to excited state. I want to remain in the ground state. So I could still use this direction. But when I come back, I don't need to come back to the 0th vibrational state. I can come to the first vibrational state. Now I created a vibrational coherence in the electronic ground state. To complete, I can go like this, and generate this, and this will end. Both of them are kind of looking at similar coherence, but one in the excited state, one in the ground state. This is excited state vibrational coherence. This is the ground state vibrational coherence. In this case, you are generating coherence between these two. In this case, you are generating coherence between these two. Okay, this form, now another question. Is there a condition over which, so you do pump probe, right? You all, or some of you have done pump probe. It is not easy to observe this kind of coherences. I can tell you that it's not easy. You cannot simply see these coherences. How many of you have at least done one pump probe or have seen pump probe of any kind? Yeah, at least 2 have done pump probe. Have you seen vibrational coherences? Probably you have seen. No, you have not seen. So why am I? So I can tell you can kind of go on literature and kind of search for pump probe data. There will be, I don't know, hundreds of thousands of papers with pump probe data. Everybody can do pump probe. You can buy pump probe spectrometers, but you don't see these coherences. You don't see oscillations. You only see decays. You see decays. Why is that the case? What could be the reason? So one of the biggest reason. Sorry, go ahead. Go ahead. Sorry. What is slow? Vibrational frequency is exactly opposite. Vibrational frequency is probably too fast compared to the excitation pulse. So to be able to generate a coherence, I need to have a pulse width, or in the frequency domain, a bandwidth large enough to excite these. So if I don't have a short pulse, short enough, which means it doesn't have the bandwidth enough to excite this coherence, then you will never see that. Most of the experiments, the pulse width is not short enough to kind of excite this. Now you can think of this process in a very classical sense. You take a tuning fork, okay, and push at it. If you push at a tuning fork, you don't generate all the vibrational modes of your tuning fork, right? So if you want to really excite a tuning fork, what you should do? You should hit. You should give an impulsive force. So it will generate a coherent superposition of all its normal modes. It generates a coherence. Exactly what it is. So to be able to generate a coherence, the vibrational coherence, it's true with electronic coherence too, you need to have very short pulses. Otherwise, you won't generate it. So this is the basis of what is called impulsive vibrational spectroscopy. Okay. And this is, I would say this has been kind of pioneered in the 90s by Keith Nelson at MIT. And later on, now we all use it. I'll show you some data as well. The important thing is now I can extract the Raman, the vibrational response of the system accurately using a time domain measurement. Okay. I mean, depends on the material. So if I take, for example, a material which has phonon energies to be less than 10 MeV, then you can kind of calculate Fourier transform. You can use 100 femtosecond pulses, still generate vibrational coherence. But let's say I have an organic molecule, then my vibrational frequencies are very, very large, hundreds of MeV. Then I need to have a 10 femtosecond pulse to generate. So it depends on the system. Depending on the system, you will either see or don't see. Of course, there is another important thing, is a damping. Okay, so sometimes you will not see multiple oscillations because many systems, the vibrational unharmonicity is extremely large, so the damping is extremely large. It so happens that whatever you're generating are optical phonons, and optical phonons decay by emitting two acoustic phonons. This is the primary mechanism of phonon unharmonicity in systems. Like, you assume it's the harmonic potential. It's not. It's highly unharmonic. And if you have, that's a very important pathway for your damping of your oscillation. So you might see one or two and then it dies off, especially at higher temperatures. If you go down in lower temperatures, you might still see. I'll give you an example. So this is data taken by me. So literally it's 2018, pretty old data, but it's kind of there. So what we see here is pump probe spectrum of some perovskite film. You see multiple features. There is a positive feature here. There's a negative feature here. Don't worry about it. They're evolving. They're decaying exponentially. But if you look closely on this 2D map, it's kind of very difficult to see here. There are very nice oscillations. Okay. If you don't believe me, what you need to do is fit these exponential decay functions. So you can fit these dynamics to exponential functions, subtract them off. If you do that, you'll get beautiful oscillations. So these are nice, beautiful vibrational coherences. Okay, if I take a cut along certain energy, you get beautiful oscillations. You see there is a beating between different frequencies because there are multiple phonon modes there. Okay, there is some temperature dependence. If you go at higher temperatures, the damping is larger because there is unharmonicity. So there are, as you increase the thermal bath of phonons, one of the major decay pathway for phonons is interacting with the thermal bath, as I said, by emitting two acoustic modes, and that probability increases as I increase my temperature. You see this. If you take a Fourier transform of that, that's your Raman spectrum measured in time domain, multiple frequencies. Okay, fair enough. Now there is a bit more detail to it in the sense that if I go back to this spectrum, it has a weird line shape. It has nice modulation here, nice modulation here, nothing right in between. This is a very characteristic line shape, and this can be explained using a displaced harmonic oscillator model. The way to think about it, again, I'm not going to go into detail, I'm just telling it out. If you're interested, come to me. Maybe when I give a talk on the Wednesday colloquium, I'll kind of talk a bit more on this. So if I think of my ground and excited states, especially with coupled to phonons, you draw one line here as a state, right? But actually, it's a harmonic oscillator, right? So it's a potential energy surface with a coordinate defined by nuclear coordinates of the lattice, okay, because of the vibrational coupling, okay? So there is no reason that equilibrium position for my ground state will remain the same in the excited state as well. So I'll have a potential energy surface, another potential energy surface displaced with respect to each other. This is called displaced harmonic oscillator model, and this line shape is a consequence of that, okay? And you can extract how the displacement of this displacement of this is related to what we call as polaronic coupling, and this displacement is quantified by a term called Huang-Ries parameter, and this tells you, I put an excitation in my system, how much my lattice has to reorganize to accommodate this excitation. So that's the kind of telling, right? If I go to excited state, my electron, I put in excited state, my physical coordinates of my atoms will not be the same. That's because electron is talking with phonons. That is polaronic coupling. And how much is it the displacement? You can quantify it using this experiment, which is very hard to do otherwise. Okay? Okay, good. So now let's stop the discussion about resonance impulsive stimulated Raman scattering. Sorry, there's a lot of words. It's impulsive vibrational spectroscopy, but it's also called resonance impulsive stimulated Raman scattering. I don't want to go into those details because that will open up a Pandora box, what stimulated Raman is and so on and so forth. But in general, when I'm looking at ground state coherences, you're talking about impulsive stimulated Raman scattering. An excited state is called displacive excitation. Again, I don't want to go into that details. If you're interested, we can have a discussion on that. Okay, let's go back to pump probe. So now, again, let's go back without vibrational states or anything. I have, let's say, 2 electronic states. Okay. Let's say I'm coming with my pump. My pump interaction is such that I go from 0, 0 to 1, 1, and I have this emission. Right? Now let's think not in terms of Feynman diagrams, think about the process. So as I said, when I have, let's say if I draw an absorption spectrum associated with this is just absorption. You'll have one absorption peak at omega 1, 0 and another absorption at omega 2, 0. Assume now that 2 is not a 2 quantum state. It's still a 1 quantum state. So you can access it. Okay, I have things like this. So if I now want to predict my pump probe signal, I'm generating the population here, right? I'm generating this population here. So I should have a ground state bleach at the energy of that transition, right? So I will have a feature here. What would I see in this region? Don't think in terms of Feynman diagrams. Think in terms of population. Initially, I had a bunch of population here. Okay. And I excited some of them. So some of them go away from here and they go to the first state. Right? We go to the first state. So I bleach my 0, 1 transition. Right? But what would I see at the energy of omega 2, 0? I would also bleach the transition because my ground state is fundamentally depleted. You agree with me on that? You agree with me on that? So I would see a feature here simply because they share a ground state. Can I write a Feynman diagram associated with this? A Feynman diagram associated with this. So I'm seeing a resonance at 2, 0, a coherence at 2, 0. That will be a Feynman diagram associated this feature. You might say, come on, man, you're not going through a population. I don't need to go through a population. I'm going through a coherence. At the end, I'm ending up at a coherence associated with this. I'm seeing that because of my excitation. Otherwise, I wouldn't be accessing that at all. Agreed? Agreed? Okay. Everybody with me on this? So whatever coherence I'm generating is because of my excitation. Otherwise, there is no way I can access that in the third order response. Come again. It can be any state, some second electronic state. I don't know. That I don't care about what physical character, what is the origin of this. It can be any state. The only thing is the first and second state have a common ground state. No, nothing. 1 and 2 share a common ground state. 0. That's all. There can be anything. There can be the 2 vibrational states of an excited state, for example, or 2 different singlet triplet states, for example. I don't know, with mixed character, or something else. A singlet state and a charge transfer state. It doesn't matter. There are 2 states in the excited state, which are coupled to ground state, which means in absorption I see 2 peaks. That's all I'm starting out. Okay. Fair enough? Fair enough? Okay, so I can kind of say, okay, I have this excitation, very nice. Now, I'm going to slightly change the scenario here. I'm going to erase this. And I'm going to go to a different situation where I call this 0 prime, 1 prime, and 0 and 2. Zero and 2, slightly higher. Now let's say 1 and 2 are not sharing a ground state. They are not sharing a ground state. Now let's say I come with a pump with which I photoexcite this. Now you might ask, in what situation that can happen? I could potentially have 2 different chromophores. I could have in a sample 2 different chromophores. The ground state is not common, right? And I come with a pump which is resonant with only 1. Remember, the absorption spectrum will look exactly the same. There will be no difference. Now, how will the pump probe look like? How will the pump probe look like? You're exciting this, so you will see a bleach of this transition. Everybody is okay with that? Everybody is okay with that. So you excite the state, so you will see a bleach at omega 10. But presence of this population is not depleting the population on the second molecule. So you would not see this guy. That contribution won't be there. Okay? Now let us take a scenario where the energy difference between 1 and 2 is extremely small. Or I'm interested in very fast dynamics. So when I'm using short pulses, I'll have a humongous bandwidth associated with my pulse. So I will inevitably excite also 2, even in this scenario. Okay? You agree with me on that? Okay? So in that case, because you're photoexciting this as well, in a scenario where my bandwidth is large enough, because I am interested in ultra-fast dynamics, which means I'll have short pulses, which means my bandwidth will be large, I will see both the peaks. Right? So in a scenario where I have short pulse, large bandwidth, my pump probe, I cannot distinguish between this and a case of this kind. It will have the same response. Okay, in this case, you will have this diagram. In this case, you will not have this diagram. But overall, the pump probe response is going to look similar. So if I do pump probe, for example, I'm asking a question, what are the correlations? What kind of correlations exist between different states? I won't know. So let's say I'm taking 2 systems and I'm saying I want to find correlations between 2. So I excite this, I will see bleach of this. That means there's a correlation, even though they don't share a ground state. But you can't say that because you will inevitably excite also this. Or you might see both of them, but I can explain that whole thing by considering a common ground state. There is no way to tell. So pump probe has limitation because it doesn't have that spectral resolution for you to kind of unravel these correlations. Definitely. I mean, if you have large enough, but even there, let's say I want to really look at it at very fast time scales, then okay, if this really far and separated, then you will never be able to kind of figure out. Now, I'm not saying that, I mean, let me rephrase. A pump probe is powerful. It can tell you a lot of things. I'm just highlighting one particular scenario where I won't be able to say. I'm not saying a general blanket statement about utility of the pump probe. See, also remember that pump probe fundamentally adds up all correlation functions. And especially in a multi-level system, that is a lot of Feynman diagrams, which kind of we can already think about how much ambiguity that can bring in. I could misinterpret data because I'm not separating out different excitation pathways. So that's a kind of a limitation, apart from the fact that you can never measure a coherence exclusively in a pump probe. Okay? Yeah. Yes, you can. You can widen in time. Then you're missing out fast dynamics. I want to look at very fast dynamics because anything beyond 1 picosecond is boring for me. Right? No, there are a lot of interesting things happening, all time scales. I'm just saying that here I'm interested in, especially when I'm looking at quantum correlations. That's one buzzword that is being used, right? So if I have two quantum states which are completely different, can there be some quantum correlations that exist between these two states? This was, for example, a big question, especially in the context of light harvesting centers in photosynthetic systems, which Krishna and I were discussing just a few minutes back during the break. That was a big problem. Like, there are multiple, like hundreds of chromophores in a light harvesting center, and there seems to be some sort of communication between these different distinct chromophores. And people are trying to ask, oh, is there some kind of quantum correlation which exists between these chromophores, even though they don't share a common ground state? And if there's truly a quantum correlation existing, you know that this quantum correlation will be completely broken down within the dephasing time of the electronic excitation, which in the presence of the bath can be very fast, which means you don't have any other choice but to use short pulses. So it's very problem driven, but you can kind of see the context. Okay, so to kind of overcome that, we want to go and expand out our measurement capability. So we are going to talk about 2D spectroscopy. So we'll talk about what are those two dimensions. So usually this is similar to a 3-pulse experiment. There's no longer a 2-pulse experiment. Remember the box car geometry. You have 3 pulses coming in as, from the edges of a square, right? Incident on the sample. And you could create, depending on the time ordering, rephasing and non-rephasing pathway. Rephasing will be K1 plus K2 plus K3. Non-rephasing will be K1 minus K2 plus K3. Right? So if I were to draw the pulse sequence as a function of time, you'll have your first field at initial time, that is E1, then you wait certain time, let's say tau 1, and then you come with your second pulse, E2, then you wait some time, tau 2, and then come with the third field, E3, then you wait some time, but you integrate over tau 3 and observe. The way to think about this is that here, for example, for rephasing, you generate a coherence, which is probably decaying. With second field, you project that coherence onto a population, which is probably decaying exponentially. Then with the, sorry, I should do more, decaying. And with the third pulse, you kind of project it back onto a rephasing signal and then observe. That's my polar. I'll show you a better plot than that. My artistic skills are not ideal. But Always remember in 2D you're measuring some kind of time integrated intensity using a slow detector. So in 2D spectroscopy, as I kind of already alluded to you, that along with your signal, you'll also send another pulse, local oscillator. I'll show you the diagram, but you kind of visualize your boxcar, 3 pulses are coming, right? The signal is emitted in the 4th direction. But along with that, I will also send another pulse, a weak intensity pulse, whose amplitude and phase I know, I characterize. I call this my local oscillator. Okay. So at the detector, when I time integrate this, my emitted field as well as this local oscillator will interfere. I time integrate, I'm not time resolving it, but it's going to interfere. So my signal will be an integral of the field of my local oscillator, which is a short pulse, but nevertheless it's there, plus I times the 3rd order polarization, which in this case is this. That is what you're measuring at the detector. To kind of show that this is approximately equal to some background coming from the local oscillator. So you kind of see your signal lifted up by the intensity of local oscillator. The local oscillator is actually nice because sometimes if I don't have my local oscillator, the signal, even though it's background free, it may be close to the noise floor of my detector, which is kind of cumbersome. So you want your local oscillator intensity will kind of move it away from the noise floor, the detector, so that you can easily measure it. So it's actually helpful. There are other problems with it. We'll not talk about that now. And plus 2 times imaginary part of the product between my local oscillator and my 3rd order response. Now remember, this is going to be related proportional to the 3rd order impulse response function, which is a function of tau 3, tau 2, and tau 1. Destructively, you mean to say? Signal will get suppressed because of local oscillator. Why would that be? Oh, the large signal will kind of overwhelm. Yeah, because but the good thing is, the first thing, the local oscillator should not be like immensely intense. It will be a weak thing. You actually have to attenuate your local oscillator substantially before sending it, which is something experimentally we do. And it will not be like 100 times more than your signal. It will be a factor of 3 or 4 more than your signal. So it's kind of slightly elevates. It's not like bringing it right from the thing, but kind of elevates it. But more importantly, it gives you access to the phase of the signal, which is the nice thing. You really measure an interferogram. So because without that, you would want to measure, you will measure a spectrum, but now you will actually measure a spectral interferogram with which you can now extract the spectral phase, because you know the phase of the local oscillator, which you would have characterized using frog or spider or whatever you want. Yes, it will be a factor of 2 or 3 more. Usually nonlinear response, I mean, it'll be surprising how strongly emitting these are, especially with the short laser pulses. Now, there are samples where it will be very hard to see a signal, and I have gone through some really weakly nonlinear samples, and it's painful, physically, mentally, emotionally. But it is very good samples. You choose your right sample, you should get very good nonlinear response. Okay. Okay, so now you have technically 3 times, but you're really time integrating over tau 3. So it's not really a variable for you anymore. But you have tau 1 and tau 2. You can vary these two, right? You can vary these two. So remember, you are going to measure the signal at a frequency omega 3. I'm going a bit random here. So you will measure a signal omega 3. I'm going to draw here. So on one axis is my omega 3, which is the basically frequency at which my nonlinear polarization is emitting, the final interaction. If I'm projecting on 0, 1 coherence, that's the frequency it's emitting, right? Okay. Now what I do, I have this tau 1 and tau 2. If I vary tau 2, what am I doing? I am accessing different population times. Because remember, after my second interaction, I'm creating a population. There's no coherence anymore. I'm creating population, and that population is evolving. So if I change tau 2, I'll go to different population delay times. Similar to what you do in pump probe, is equivalent. Right? This is exactly the pump probe delay. It's exactly the pump probe delay. Your E1 and E2 happens to be the same pulse in pump probe. Here, the only thing that we are doing is that taking that pump pulse and making it 2, E1 and E2. And you have a delay between them. Now, what happens if I scan the delay between them? I am actually measuring my first coherence that I'm generating. I'm kind of accessing that. Right? I'm accessing this part. In fact, if I do the experiment, you will see an interferogram oscillating. And if you take a Fourier transform of that, that will be your second axis, which we call omega 1. This happens to be the Fourier transform along tau 1. Fourier transform along tau 1. So you scan, the experiment is, you scan the delay bit, you keep the same tau 2 for now, same tau 2, you don't change tau 2. You scan the delay between the first and second pulse, and you measure nonlinear response. Okay? You put that spectrum, which is as a function of omega 3, as a different time delays, and then along that tau 1 direction, you take a Fourier transform. Okay? Then you will get this. It's a 2D spectrum. What is omega 1? Omega 1 is the frequency at which your first coherence is emitting. Is the frequency at which the first coherence is emitting. So it is referring to the absorption. It is referring to the absorption. First coherence is the absorption event. Right? This one is the frequency of the emission of the nonlinear polarization. Is the frequency of emission of the nonlinear polarization. So I call this emission. So let me rewrite this. So what you do in an experiment, you measure the spectrum of omega 3 as a function of tau 1. Then you do a Fourier transform. Then you will get omega 3, omega 1. Okay? Everybody fine with this? Okay. So let's, another thing to note, you know that non-rephasing will be plus K1 minus K2 plus K3. So if I write to frequencies, this will be omega 1 minus omega 2 plus omega 3. And rephasing is minus K1 plus K2 plus K3. So this technically corresponds to a frequency which looks like omega 1 plus omega 2 plus omega 3. It's not really a negative frequency. It simply means that the complex conjugate of the field, right? So it's not that you have negative frequencies, doesn't make sense. It just shows it's a complex conjugate. So to kind of distinguish rephasing and non-rephasing, typically non-rephasing is plotted in this quadrant with positive frequencies for both. This is non-rephasing. And rephasing, because of negative frequency, it's a normal, it's kind of a convention. You put omega 1 negative, omega 3. This is rephasing. It's just a convention of how you plot the 2D. Shows up. Okay. Okay. So this is a typical experimental setup, realistically. So these are the 3 pulses which are incident on the sample. You send a local oscillator, you see this wheel. It has, we actually made this, we got some kind of silver coated on this to kind of reduce its intensity. It should be weak. It should not be interacting, otherwise it's going through the sample. It can interact and create another force field interaction, other nonlinearities. It's a problem. In fact, now we are currently working on an experimental setup where we don't let the local oscillator go through the sample, because we want to kind of eliminate any possible artifacts that can come because of the interaction of the local oscillator with the sample. That's an experimental challenge. You see the fourth one, 4-wave mixing signal was emitted in the direction as the local oscillator. You kind of block the other 3 and we collect it. And this is actually a data, some interferogram. This is basically the interferogram measured here, intensity as a function of wavelength. Of course, you do this at different delays between my first and second pulse. Okay, I measure that. A Fourier transform, I should get a 2D map which looks like this. You see the problem? The community has different, let's say, conventions, which I hate. There is no agreed upon convention. So this, I took it from an annual review of physical chemistry from Fuller and Olivier, and they use a different convention than the rest of the world. Doesn't matter. You have one excitation or absorption axis. You have one emission axis. These are the 2 axes which form the 2D plot, and then third axis, which is the color map, is the intensity of the signal. Okay. Remember, you're measuring the spectral phase, so you have access to both real and imaginary parts of your response. So you have the amplitude and phase of your nonlinear response because of the interferometry. You have access to that. Right? Okay, so you can plot the real value of your 2D response, your imaginary value of your nonlinear response, as well as the absolute value. You can issue that way. Okay, so you kind of see a lot of features here. First of all, a 2D map. Think of a 2D map. There's always something on the diagonal, right? There is something on the diagonal, and there are some features of diagonal. So we need to understand what are these. So now it's like, think of it like this. In a sense, in pump probe, you had only one axis here. We had only the detection axis. We were integrating along the excitation axis. We didn't have that spectral resolution along the excitation, right? And that was a problem, because we didn't have a resolution along the excitation axis. We were not able to distinguish whether we saw 2 bleach signals because we had common ground states or there is quantum correlation. Agreed? Agreed on that? Right? So here, on the other hand, we have that resolution. We have that second resolution of the excitation axis. So it's kind of 2D map. And so we're kind of separating out different excitation pathways. They're not overlapping anymore. They're kind of separating it out. That's the strength of a 2D spectrum. Let's take a simple case, again, of a 2-level system. 2-level system, but let's say it has, no, it's not a 2-level system, 3-level system, but a 2 quantum state. Let's take a simple case where I have a ground state, I have an excited state, and I have a 2 quantum state. So remember, a 2 quantum state is usually not accessed from the ground state. By symmetry, it's forbidden. Okay, the 2 quantum states are not accessible from ground state. They can only access them. So technically, I would say if I photo excite this in a pump probe signal, I would see a bleach and a photo-induced absorption. This will be my ground state bleach. This will be my photo-induced absorption. So typically your spectrum in pump probe, this is energy scale. So you will have your bleach. And usually because of unharmonicity, 2 quantum state is slightly lower than twice the 1 quantum state. It's called some kind of interaction will reduce it. So usually the photo-induced absorption band will be on the lower energy side. Okay, so that's a kind of picture that we kind of come up with when you think of pump probe. Now what we can do with 2D is a bit more detailed, right? So you kind of map it out like this, whenever it comes. You map it out like that. For there's a lot of detailing there. You will later see how homogeneous and inhomogeneous broadening kind of manifest on 2D line shape, but that's kind of line shape. Now you will say, come on, there is no real advantage in just looking at these 2 features. I can do pump probe and do this. I agree. 2-level system, it's kind of boring, although this can give something which pump probe cannot give. But you also know that 2-level systems hardly exist in this world, right? There are multi-level systems. So because of that, we can kind of complicate. Now, if I take a more complicated scenario, okay, this I want to leave as a kind of homework. Tomorrow we can do this. As this complicated scenario, I will send it via email tonight, probably. And I will also tell you that this is the kind of 2D spectrum you will get from that. Now, what I want to kind of note is that there are features which are labeled from 1 to 8, and these are very specific excitation pathways that we are able to spread out and separate, which is the biggest kind of advantage of doing 2D spectroscopy. Okay. More importantly, you will see, we'll not do it today because I want you to think about this. You will see that the diagonal features correspond to the population or ground state bleach signatures. You can have excited state features which are negative right next to absorption features. Simply the way to think about it is that I'm pumping here and now I see something at lower energy, negative sign. It's a photo-induced absorption. I pump here, I see at that energy, that's a ground state bleach. Cool. The most important thing, or one of the most important things, are the cross peaks that come, which means I pump here and I see something on the other energy, or I pump here and I see something at lower energy. Okay, that is something which is remarkable. In the absence of quantum correlations, you will only see cross peaks, which are coherences between the 2 states mediated by a common ground state. Now, if I have 2 systems where there are no correlations, they don't share a common ground state, then they will look something like this. 2 states, no cross peaks, because there is no way the 2 states are talking to each other. There is no coupling. Okay? I could have evolution of coupling by energy transfer schemes. We'll talk about that later. But I will only see cross peaks. Either the system or 2 states are sharing a common ground state, or if there is a quantum correlation between them existing. Okay? So we will kind of dig deeper into this, kind of write down all the various Feynman diagrams. Tomorrow as well as Saturday, we will also try to do some QDPy to kind of simulate some line shapes to some response functions to kind of see. These are some examples from literature. Some of the early ones, 2D maps, I would say this one was done, 2D was first done, I would say, in infrared by Tokmakov group. They were really the pioneers in early 2000, real 2D spectroscopy on this molecule. Don't ask me why this molecule is interesting. It is supposed to be very interesting. and they see correlations. And later on, I think Kandif did on gallium arsenide quantum wells. We will kind of go over this in detail, kind of what these spectral features correspond to, so on and so forth. These are some of our spectra done on 2D perovskites. This is absorption spectrum, and these are 2D spectrum. There are multiple features here. There are cross peaks here. There's also some features. Line shape here, right? This is, by the way, rephasing. So the absorption energy negative, as you can see, the rephasing spectrum. Before closing, I want to just highlight one thing. So I take this 2D spectrum. In the absorption, you can kind of see 4 features in the absorption spectrum. This feature is hardly visible, but clearly these features are visible. That's our different excitonic states. And correspondingly, you see features very cleanly along the diagonal, right? These are the ground state bleach features. Now, because I can, why not? I took a cut along the diagonal and along the anti-diagonal, okay? If I take a cut along the diagonal, let's focus only on this region. You can also see that here. You see one peak, the first peak, second peak, third peak, and the fourth peak is kind of very small and can be seen as well, okay? And if I take an anti-diagonal cut, you get pretty nice line shape. Now, what do you observe in terms of line shapes between the diagonal cut and anti-diagonal cut? In terms of the line shape, what kind of mathematical form it could be? When I say Lorentzian, Gaussian, what do you think? Diagonal is, anti-diagonal is perfectly Lorentzian. And diagonal, I can tell you, is perfectly Gaussian. Anti-diagonal is Lorentzian and diagonal is Gaussian. And you already know from what we discussed earlier and also previously, homogeneous line width will lead to a Lorentzian broadening, and inhomogeneous broadening will lead to a Gaussian line width. So 2D spectrum intrinsically, for some reason, as of now, I don't know yet, because I have not told you. I mean, I know it, but I have not told you yet. For some reason, is able to separate out my homogeneous and inhomogeneous line width as diagonal, anti-diagonal line widths. It's kind of a bit more complex. Hopefully, I'll try to convey why. Let's see. But another biggest advantage, apart from finding correlations between different excited states, another important utility of 2D spectra is to separate out homogeneous and inhomogeneous line widths. Okay. In the next class, we'll go over these 2 topics again, take 2D spectra and figure out what these features correspond to, write out the Feynman diagrams if you have time, assume some kind of state to begin with, 3-level, 4-level system, and predict what a 2D spectrum would look like, and write out all the Feynman diagrams. If you're lucky and if you're chosen reasonably well in the 3-level, 4-level systems, you might have to write down 64 diagrams, but that doesn't matter. But that is one part of that. So the important thing in that is that you can start finding correlations between different excited states, and that correlation can simply be presence of a common ground state, or it could be actual interactions between excited states driven by some quantum covariance. The second topic will be analysis of the line shape itself, whether especially the features along the diagonal, which we know corresponds to ground state bleach features. So it's only corresponding to a population term, and we will analyze, we'll try to understand why the line shapes could possibly be Gaussian along the diagonal and Lorentzian along anti-diagonal. Okay? I mean, I could complicate life and do I have that? I don't have that here. I could complicate life and show you real and imaginary part that is even more complicated. It has very strong absorptive dispersive line shapes. If you have kind of heard about Kramer's-Kronig relationship, you can kind of manifest also 2D line shapes, which I will not be dealing with this course because it's just too much. But let's focus on this correlations between excited states and the line shape analysis. Okay.